Naming refrigerants. Instead of their complex chemical names, an easier way to refer to refrigerants is by number. The DuPont company has created an easy method of naming refrigerants, depending upon their chemical composition. 1. The first digit from the right is the number of fluorine atoms. 2. The second digit from the right is the number of hydrogen atoms plus 1. 3. The third digit from the right is the number of carbon atoms minus 1. If this number is 0, omit it. Example 1. HCFC 123. CHCl2CF3. Dichlorotrifluoroethane. Number of fluorine atoms equals 3. Number of hydrogen atoms plus 1 equals 2. Number of carbon atoms minus 1 equals 1. Thus, HCFC 123. The number of chlorine atoms is found by subtracting the sum of fluorine, bromine, and hydrogen atoms from the total number of atoms that can be connected to the carbon atom, or atoms. Example 2. CFC 12. CCl2F2. Dichlorodifluoromethane. Number of fluorine atoms equals 2. Number of hydrogen atoms plus 1 equals 1. Number of carbon atoms minus 1 equals 0. Omit. Thus, CFC 12. The small letters A, B, C, D at the end of the numbering system represent how symmetrical the molecular arrangement is. An example is R134A and R134. These are completely different refrigerants with completely different properties. Both have the same number of atoms of the same elements, but differ in how they are arranged. These molecules are said to be isomers of one another. In the following diagram, notice that the R134 molecule has perfect symmetry. As isomers of this molecule start to get less and less symmetrical, the small letters A, B, C, D are assigned to their ends. Refrigerant blends. Ozone depletion and global warming issues have caused a need for much research on refrigerant blends. Refrigerant blends have been used successfully in both comfort cooling and refrigeration. Blends can have as many as 4 refrigerants mixed together to give properties and efficiencies similar to the refrigerants they will replace. HCFC-based blends are short-term replacements for many CFC and HCFC refrigerants, whereas HFC-based blends are long-term replacements. Azeotropes or azeotropic mixtures are blended refrigerants of 2 or more liquids. When mixed together, they behave like R12 and R22 when phase changing from liquid to vapor. Only one boiling point and/or one condensing point exists for each given system pressure. Figure 9-8 illustrates a temperature-pressure graph of an azeotropic refrigerant blend showing the refrigerants boiling at one temperature for a given pressure through the length of the heat exchanger, evaporator. Pure compounds or single-component refrigerants, like R12 and R22, also exhibit this behavior as they evaporate and condense. Azeotropic blends are not new to the HVACR industry. R500 and R502 are both azeotropic blends that have been used in the industry for years. R500 is made up of 73.8% R12 and 26.2% R152A by weight. R500 is used in some cooling systems. R502 is made up of 48.8% R22 and 51.2% R115. It has been an excellent low-temperature refrigerant since the 1960s. However, many refrigerant blends are not azeotropic blends. They are near azeotropic mixtures. A refrigerant mixture is a blend of 2 or more refrigerants that can still separate into individual refrigerants. These blends act differently because 2 or 3 molecules instead of 1 are present in any one sample of liquid or vapor. More than one molecule is always present, for example, sugar water and salt water. This is where a difference arises in temperature-pressure relationships of the near azeotropic blends versus refrigerants, like CFC12, HCFC22, HFC134A, and azeotropic blends. Near azeotropic blends experience a temperature glide. Temperature glide occurs when the blend has many temperatures as it evaporates and condenses at a given pressure. Figure 9-9 illustrates a temperature-pressure graph of a near azeotropic refrigerant blend, showing the refrigerants boiling at many temperatures, temperature glide, for a given pressure, through the length of the heat exchanger. In fact, as the near azeotropic refrigerant blend changes phase from liquid to vapor and back, more of one component in the blend will transfer to the other phase faster than the rest. Zeotropic refrigerant blends also exhibit these properties, but to a greater extent. This is different than refrigerants like R12, R134A, and R22, which, as shown in previous units, evaporate and condense at one temperature for a given pressure. Near azeotropic refrigerant blends may also experience fractionation. Fractionation occurs when one or more of the refrigerants in the blend will condense or evaporate at different rates than the other refrigerants. This different rate is caused by the slightly varied vapor pressures of each refrigerant in the blend. Fractionation will be applied in detail in Unit 10, System Charging. Zeotropes, or zeotropic blends, also have temperature glide and fractionation, but to a larger extent than near azeotropic blends. The terms zeotropic blends and near azeotropic blends are used interchangeably in the industry because they both have temperature glide and fractionation. R numbers for the blends. The 400 series blends are the near azeotropic zeotropic blends. If a blend has an R410 designation, it is a near azeotropic blend. The 10 indicates that it is the 10th one commercially produced. They all have temperature glide and can fractionate. The 500 series blends represent the azeotropic blends. R502 would represent an azeotropic blend. The 2 means that it was the second one produced on the market. Blends can also be represented by the percentage of each refrigerant that makes up the blend. The refrigerant with the lowest boiling point at atmospheric pressure will be named first. For example, a blend of 20% R12 and 80% R22 would be represented as R22/12, 80/20. Because R22 has the lowest boiling point, it is listed first. Blends can also have capital letters at their ends. The capital letters at the end of R401A, R401B, and R401C mean that the same 3 refrigerants make up these near azeotropic blends, but their individual percentages differ.